Okay, so that's one of the 3 problems that I want to do today. The next one is to say, well, what if we got our starting amounts through combustion analysis? Combustion analysis is one way to get data for a molecular compound, for a covalent compound. And this is the general process. So we have something that contains only nonmetals, and typically for molecular compounds, for covalent things, we could write something called a molecular formula, and it starts with C and then H and then all the other elements in alphabetical order. Typically, oxygen is going to be another element, but in some of the problems you're going to see on your worksheets, there will also be nitrogen and sulfur. So W, X, Y, Z, ran out of letters, T. So when we're looking for something like this, we're gonna go through a process where we combust it, we burn it, and all the carbon is gonna end up being carbon dioxide, and all the hydrogen will end up as water. Nitrogen will end up being nitrogen dioxide, and sulfur is typically sulfur dioxide. So these are going to be the products of complete combustion. What is complete combustion? That means you added enough oxygen so that every nonmetal, carbon, hydrogen, nitrogen, and sulfur, had as many oxygens as was normal and stable for it. So complete combustion means I've taken fuel, I've added an excess of oxygen, given it a spark to start the fire, and the products are carbon dioxide and water, typically, unless there's nitrogen or sulfur in your compound. So I'm just going to focus on carbon dioxide and water from here on out in this video. Specifically, I want to focus on, you have a compound that has carbon, oxygen, and water. Why these 3 things? Because this is most typical, you're going to run into this the most, and also once I explain this, you'll know how to do the other calculations with sulfur and nitrogen. Okay, so what happens is that fuel is sent through a container with oxygen, and so they're pumping oxygen in, and oxygen is being pushed through a system of basically tubes. And in one of the tubes, it goes through something that absorbs carbon dioxide. And so oxygen is pushing the whole gas that is produced from the combustion through that tube. The only thing that is pulled out of this flow of oxygen gas pushing the products of combustion through is carbon dioxide. And then they have another desiccant, absorber, that's only going to absorb water. And so what ends up coming out after the whole gaseous mix goes through is just more oxygen. So there's always oxygen pumping the products of complete combustion through the system. And then somebody will take this tube and they'll know the mass before and the mass after. And the difference in mass is the carbon dioxide that had been absorbed. And that carbon dioxide, its carbon came from the reactant. So I can use the difference in mass to know how many grams of carbon dioxide are present. And then I can know moles of carbon dioxide using the molar mass, and moles of carbon using the formula, 1 carbon for every CO2. And now I have the moles of carbon that I need for the molar ratio. In a similar manner, this other tube is way before and after. And the difference in mass here is grams of water. Water vapor sticks, and we can go to moles of water. And then for moles of water, we know there's 2 hydrogens in every 1 water. We use that 2-to-1 ratio to get to moles of hydrogen. So now we have 2 of the 3 things we need to do the molar ratio, but the third thing we need is oxygen. And that's the part that is trickier and different with combustion analysis. To figure out how much oxygen, we're going to have to start with, we'll have to be given a starting mass, so a sample mass, and then we'll subtract out the grams of carbon, and we'll subtract out the grams of hydrogen, and what we're left with is grams of oxygen. We change that to moles of oxygen, and now we have the 3 moles that we need to do the molar ratio to come up with the formula. Does that make sense?
Yes.
Thank you, Kylie. Okay, so I'm going to erase this screen and start doing the problem. The problem that I want to do is the first one on your homework assignment, that is combustion analysis. So on the more empirical formula page, combustion analysis, do this homework, submit it. I'm doing number 1 for you. If you have that handy, that will probably help. Okay, so let's say we were given this problem. There's a combustion analysis of a formula that contains carbon, hydrogen, and oxygen. So we have a covalent compound with these 3 elements. And we're told at the beginning that the mass of the sample is 3.200 grams. When the sample has gone through combustion, it yields 4.797 grams of carbon dioxide. It also yields 1.306 grams of water. So I'm going to do 2 things on one set of train tracks. On the set of train tracks for carbon dioxide, I'm going to go from grams of carbon dioxide to moles of carbon dioxide to moles of carbon. See what that number is. And then I'm going to continue on to grams of carbon so I can subtract the grams of carbon from the sample. And then for water, the same idea. Grams of water to moles of water to moles of hydrogen, remembering that there's a 2-to-1 relationship. Get that set of moles, because I need that for my molar ratio. But I am going to continue on and get to grams of hydrogen so that later I can subtract that. And my reason to do that is to come up with the grams of oxygen so we can go to moles of oxygen. So you can go ahead and get started, and I will too, and then we can compare notes. So now that I have the amount of moles of each of the elements, I look for the smallest number. The smallest number is carbon. The carbon and oxygen are pretty much the same number. But because carbon is the smallest number, that's the one I'm going to divide by. I would like to point out what the most common mistake is. And the most common mistake in these problems is missing this step. Students will forget that there's 2 moles of hydrogen for every mole of water. Okay, so for carbon, for hydrogen. So I need the moles of hydrogen per mole of carbon isn't a mistake. That's the ratio that is right. And I have to decide, what does 0.3298 look like? And I think it looks like a third. So what I have is carbon, hydrogen, oxygen, 1 mole of carbon for every 1 mole of oxygen. But for hydrogen, I have 1 1/3. The ratio I need to multiply by is something like 3/3, 1 in the form of 3/3, so that I end up with a 4 there and a 3 here. So you may prefer to look at it this way. I'm going to take this whole idea, and because that looks like 1/3, I'm going to multiply everything by 3. And when I do that, what I get is C3H4O3. And so that is the empirical formula. But it may not be the molecular formula. So the extra information that I'm going to need is the molar mass. And then I'll need to sort out the empirical mass, compare it to the molar mass, and see if this is the right formula or if this is like the lowest common multiple. It's not the correct number of each thing. So I'm going to clear off the top of the page to make room for that. So the molar mass that is given in the problem is 176 grams per mole. And that would have been determined through a different kind of experimentation. The empirical mass is 3 carbons plus 4 hydrogens plus 3 oxygens. So add up all those molar masses and I get 88 grams per mole. And that ratio is 1.998. That sure looks a lot like 2. So the molecular formula is twice as many everything as the empirical formula. Questions? Alrighty, so that's one kind of problem, how to use combustion analysis to come up with the molecular formula for a covalent compound.